and he'll be speaking on connectivity of joins,
Cohomological.
cohomological, quantifier elimination, and an algebraic Toda's theorem. So thanks for being here.
Thanks, Caroline, and thank the organizer for inviting me to give this talk. And just by looking at the auditorium, I feel jealous and not to be able to be there in person, but well, it's what it is. So this talk is going maybe will be a little bit could be off the topic of mainstream model theory, but I want to convince you of a certain result which I think of as some kind of a cohomological version of quantifier elimination in a sense that I'll explain, and its applications. So there are several aspects of this. The main tool comes from a connectivity result, which is a result from algebraic geometry. And then there is an application of it in a result which comes from computational complexity theory, namely this Toda's theorem. And in this talk, I will focus mainly on the quantifier elimination aspect, and I'll mention something about the other two parts. And please feel free to interrupt me if you have any questions. And unfortunately, I have no means of writing because I'm giving it from a laptop, but I'll try my best to answer the questions in words. Okay. Already I have a problem. Okay. Okay, so that's the outline. So topological methods in model theory has a history. I just listed an incomplete list of applications of topological or cohomological methods in model theory and combinatorics. For example, certain proofs of bounding the Vapny-Chavanenkis densities of definable families in O-minimal structures. And then more recently, in a joint work, again with Deepam. Oh, by the way, I forgot to mention, all the things that I am going to talk about today is joint work with my colleague Deepam Patel at Purdue. And with Deepam, we also proved bounds on VC densities of definable families in ACVF algebraic closed value fields using topological arguments. Then in incidence combinatorics over the reals, particularly polynomial partitioning method uses topological methods, bounding the number of distinct topological types in definable families. And then, so these are applications in model theory, but then there are applications in the larger world of combinatorics, like topological helitype theorem, all the recent work on combinatorial Hodge theory of Jun Hu and Adiprasito and people like that. And then there are, I'm sure, many others. And today I'm going to talk about the topic of interest. And everything in this talk is based on this paper with Deepam that appeared in Selecta last year. So first of all, let me just recall quantifier elimination in the theory of algebraically closed fields. And algebraically, so the entire talk will be about algebraically, the underlying field will be algebraic, assumed to be algebraically closed, but of arbitrary characteristic. So, so we all know basically this is a Chevalier's theorem, or that the theory of algebraically closed fields admit quantifier elimination. So that if you have any first order formula involving quantifiers in the language of the field K, then there exists a quantifier free formula equivalent to it. And I write this equivalence as the realization of phi is equal to the realization of phi prime. So in
Sorry, we have a
Oh.
question.
Yes, please. Go ahead.
You say the realization where?
I mean, so in K raised to the number of variables in Y.
But you're talking, but I thought you said you're doing things overall characteristic or something. I mean, this is okay. Yeah,
It's
okay,
a-
never mind. Sorry, if that's what you mean, fine. Thank you.
Yes. Yeah. Yeah. So a K is a fixed algebraic closed field, but of whatever characteristic K. So, so we are going to, because of limitations of our results, we have to restrict our attention to what we call proper formulas. So our proper formulas are positive Boolean combinations, by which I mean just disjunction and conjunctions, but with no negations, of atoms of the form p equals 0, where p is a multi-homogeneous polynomial with a fixed common block structure. So that means that this p equals 0 defines an algebraic subset of a product of projective spaces over K. So that's what we'll call a proper formula. So all the varieties that are going to appear are going to be complete varieties or compact, if you just want to think about complex numbers. And so just like a first order formula defines constructible subsets of some affine space, a proper formula would define algebraic subset of some products of projective spaces. So if I write products of pn's, but these n's could be different depending on the blocks. And now the shape of our theorem, what I want to say as a cohomological quantifier elimination is going to be as follows. So given such a proper formula, possibly quantified over algebraically closed field, we produce a quantifier-free formula, C prime. And here maybe answer to the question is that this construction, this J of C this construction does not depend on the characteristic. So you give me a formula C, I produce J of C, which is going to be quantifier free and also proper. Well, this is not equivalent to C in the strict sense of quantifier elimination, but C prime is going to be related to C via cohomological invariant, which I'll define a little later, but it's closely related to the Poincaré polynomial, and which we'll call the pseudo-Poincaré polynomial. So it's a polynomial in one variable with integer coefficients. And so the statement, the shape would be that this invariant of C can be recovered from that of the quantifier free C prime using only arithmetic over Z. More precisely, there exists a map which takes polynomials to polynomials and which just depends on the sequence omega of quantifiers and the block sizes in the given proper formula C, and not on the actual formula, and such that the following equality holds, that Q of C, which Q you should think of as a Poincaré polynomial of the realization of C, is equal to the Q of the realization of C prime up to this map here, which I'll denote by F omega. So none of these have been defined as yet, but that's the shape of what I want to prove. And the theorem could be thought of as quantifier elimination once we substitute the realization map, this R of a formula, which takes formulas to constructible sets, as in classical quantifier elimination, by the map Q, which takes formulas to polynomials. And while we have an absolute equality in the classical case, we have a kind of pseudo equality, well, not an equality, but up to this map F omega of the Poincaré polynomials of Q of C and C prime. So in the case of sentences, meaning when there are no free variables, we obtain that C is true if and only if f omega this of Q of C prime equals 1. So this is what I want to call as cohomological quantifier elimination. Well, the first question that one might have is what is gained? And in fact, it looks like nothing is gained, because after all, you have quantifier elimination. So if C prime was to be taken as a classical what you get by classical quantifier elimination, then of course Q of C, the realization of C and realization of C prime would be the same. So their Poincaré polynomials would be the same. So what? But the main advantage of this variant is becomes apparent only when one views it through the lens of kind of complexity. So in the classical quantifier elimination, the quantifier-free formula can be potentially and is unavoidably much more complicated than phi. So for instance, the degrees of the polynomials which appears in the atoms of the quantifier-free could be much, much bigger than the polynomials with atoms appearing in atoms of phi. And there is no direct way of producing this quantifier-free formula from phi without using algebraic constructions, such as taking resultants. So here's a basic example coming from geometry of how the blow up of complexity happens when we pass from phi to phi prime. So this is the example of the incidence variety. So here V of dn is the vector space of polynomials of n plus 1 polynomials, direct sum of vector spaces of polynomials in homogeneous of degree d in n plus 1 variables. So that's just a fancier writing, is each element of VDN is really n plus 1 homogeneous polynomial of degree d. And Wn is just kn plus 1. And let phi dn of f0, f and x. Now here we have a block structure. So I'm going to projectivize this VDN. And so f0 to fn should be thought of as homogeneous coordinates in the projectivization of VDN. And then x, which is homogeneous coordinates with n plus 1 variables. And let phi dn be this proper formula, that there exists x such that. So what this formula is, first of all, this is a proper formula because each one in the conjunction is bihomogeneous in the fi and in the f's and x. And all this formula says is that there exists a projective 0, common 0 of the n plus 1 polynomials in Pn. F0. So normally, of course, there should not be a 0. So for a hypersurface in the projectivization of EDN, we'll have those tuples which have a common 0 in Pn. So xdn, the realization of VDN is the subvariety of the projectivization of VDN times projectivization of Wn. And suppose and then let P sub dn denote the projection onto the factor corresponding to the polynomials. So now XTN, as I said, is a hypersurface in P of VDN, and it is defined by a classical resultant of the forms F0 to Fn. Of course, one has to be a little careful because the resultant should be multi-homogeneous, but here the way I define the projectivization, I just made them into one big projective space. But in any case, this hypersurface has degree which is of n+1 times d raised to n. And this is exponentially large in n. So that means if you want to eliminate the quantifier from this proper formula, then the quantifier free formula will need to have a polynomial of degree at least exponentially large in the degree d. So this is what I mean when I say that in the classical quantifier elimination, the quantifier free formula can be much, much bigger than the given formula. So yeah, so the quantifier free is r equals 0, but it has this big degree. And if one measures the so-called complexity of a formula by, say, the maximum degree of the polynomials appearing in it, or even the sum of the degrees of the polynomials appearing in it, we see that while the complexity of phi dn is bounded by d, that of phi prime dn is exponentially big. Now, in contrast to this, in our theorem, where I have not yet defined this J, but in this, the complexity of this quantifier free formula that will be produced is bounded still by the degree of the original polynomial. And moreover, in this particular case where just one existential block, the operator f omega is very simple. It is really the operator that first multiplies a polynomial by the polynomial 1 minus t, and then truncates it to a polynomial of degree with dimension of vdn minus 1. So let me just go back to the shape of the statement. So J of C, which you have not defined, is going to be some simple formula involving polynomials of degree d, and f omega is in that particular example a rather simple operator, which is multiplying the given polynomial by 1 minus t and then truncating it.
We ask a question. So I just so projection of a closed set in this case is still a proper set, right? So I mean, not quite that. Do you need to introduce this pseudo-Poincaré polynomial because you want to look at the cross characteristic, or is it?
No, this pseudo-Poincaré is just an artifact of the proof, but it has nothing to do with the fact that it's true for all characteristics. But of course, I have to say one thing that I should be careful about. So these Poincaré polynomials is going to be defined in terms of some cohomology theory, which should hold for R over fine positive characteristic. And the cohomology theory that we are going to use are L-adic Ital cohomology, where L, this of the L-adic, should be a prime not equal to the characteristic of the field. So when I say it's independent of the characteristic, there is this glitch that the L in the L-adic should be not equal to P. But otherwise, and this L is hidden inside the pseudo-Poincaré polynomial.
Thanks.
Okay, and this last feature is going to be used in the proof of the Toda's theorem, which I'll mention a little later. maybe let me just say a little bit about what Toda's theorem is. So this comes from really classical complexity theory involving Turing machines and so on. And in this classical complexity theory, there is a clear analog of the Dean's hierarchy in logic, which is usually called polynomial hierarchy. And it is defined in terms of alternations of quantifiers. So a fixed existential quantifier, well, if there are no quantifiers, that corresponds to the class P. And if there is one existential block, then it's NP. If there's one universal block, then it's called co-NP. And then you can build up a hierarchy, and no one knows whether this hierarchy collapses all the way back to P or not. And another important object that's studied is computational complexity of functions. So usually computational complexity of languages are sequences of subsets of 0, 1 to the n. But here one talks about functions, and the Valiant introduced this class called sharp P. So this is an analog of P, but for functions. And it can be defined, even though this is not the definition that I prefer, as the set of functions which counts the number of accepting paths in some non-deterministic Turing machine. And Toda's theorem is one of the basic theorems of computational complexity. And it says that this counting class sharp P is very powerful, namely that, in fact, any language in the polynomial hierarchy, that means any language, not just in P, but in NP, co-NP, and the higher levels, can be decided by a Turing machine in polynomial time, provided it's given access to an oracle, which has the power to compute a function in this sharp P. So I understand this is a rather vague because I have not defined anything, but you should just keep in mind that it says that if you have a black box that can compute function sharp P, then in fact, using this black box only once, you can decide any membership in any language in the polynomial hierarchy. So normally it is stated like this. And so why does this enter our world? Well, there is a generalization of these classical complexity theory from Turing machines to computations or arbitrary structures. And this goes back to work on the model theory side. I think Bruno Poisson has a original paper on it, but then it was developed by Bloom, Shub, and Smale, who defined machines over real and complex numbers. And then once you have the notion of P, class P over, let's say, over the reals or over the complex numbers, then since the polynomial hierarchy is defined in terms of alternations of quantifiers, then there is an obvious analog of what polynomial hierarchy should be. But then these counting functions, well, one way of thinking about another equivalent definition of sharp P is these are functions. Sequence of functions is in sharp P. If one can find a language in P and a projection, let's say, to half the coordinates, such that the function values is counting the fibers of the projection map. Since everything is over this 0, 1 raised to n, fibers are all finite. And so this gives us, so counting the number of elements, cardinalities of the fibers is a map ending up in Z. So once you have this picture that sharp P corresponds to functions which count fibers, then in the Bloom-Shub-Smale or over these more general complexity theory, let's say over real or complex numbers, you can ask yourself, what should it mean to say a counting function be in sharp P? So you want to say that it should count fibers, but the fibers would now be constructible or semi-algebraic subsets. And so one natural, reasonable choice of what it means to count over R or C, well, the first thing that comes into mind is maybe the count should be the Euler characteristic. But in fact, if you which is a good reasonable choice, but we cannot prove theorems with this choice. So we took the notion of counting to mean computing the Poincaré polynomial, which has more information than the Euler characteristic. And then replacing the notion of counting fibers by computing the Poincaré polynomial of the fibers, we can define an analogous class sharp P over real and complex numbers. And we could prove real and complex versions of Toda's theorem with work with theory and with real case, and by myself in the complex case. So this was happened about 10 years ago. So in the current work, we can extend this, since we now have the required topological argument over arbitrary fields of arbitrary characteristic, we can prove an algebraic version of this Toda's theorem. And I write it this way, which looks a little different from Toda's theorem because we want everything to be algebraic. And so this one on the left-hand side just denotes the characteristic function, which is a constructible function on a product of projective spaces. And on the right-hand side is the class sharp P. So I'm not going to say much more about this theorem than this. So the only thing here is because of the availability of the required topological results over arbitrary fields, we can now prove an analog of Toda's theorem over arbitrary characteristic. As long as you believe that counting is reasonably replaced by computing Poincaré polynomials. Okay, so now I want to make at least a precise statement of this cohomological quantifier elimination that I had introduced before. So here's what the pseudo in the pseudo-Poincaré polynomial. So given any polynomial with integer coefficients, we break it up into the even and the odd parts. And then for any subscheme of product of projective schemes, projective spaces, we denote the pseudo-Poincaré polynomial to be the even part of the Poincaré polynomial minus t times the odd part of the Poincaré polynomial. So it's something that you can read off from the Poincaré polynomial of the scheme.
Sorry,
And then,
Anand would like to ask, what is the
yes.
Poincaré polynomial?
Yes, that's a good question. So it is just, as I said, we are assuming a cohomology theory, and it's just the sum of, so Poincaré P of V is the sum of Bi of V times T raised to I, where Bi of V is the dimension of the ith cohomology of V. And since we are going to use L-adic Ital cohomology, these would be vector spaces over QL, and it will be they will be finite dimensional. So it just records the dimensions of the ith cohomology. In algebraic geometry, the Poincaré polynomial is usually stated with signs, but we just take the just without sign. And so, and for a proper formula, then Q of the pseudo-Poincaré is just Q of the realization of V. So notice that if you have Q of Pn, so the Betti numbers of Pn from 0 to n is 1 in the even dimension and 0 in the odd dimension. So if you take the even part, so the odd part is 0 of the Poincaré polynomial of Pn, and the even part is just this. And so the Poincaré polynomial is Pn is 1 plus t square plus t raised to 4 all the way up to t raised to 2n. And the pseudo-Poincaré polynomial is just 1 plus t up to t raised to n. So that's the definition of the Poincaré polynomial, which is simple. But here I probably would not want you to digest. So now I want to define, at least state the definition of J of C. But this definition has too many indices. So I just want to point out the salient features. So first of all, here you have this block structure of W1 to Wm, X1 to Xn. These are homogeneous blocks. So the atoms would be going to be multi-homogeneous polynomial of these blocks. So in m plus n blocks. And W1 to Wn are the blocks corresponding to the free variables. And X1 to Xn are the blocks corresponding to the quantified variables. And then we have some kind of inductive definitions of these n's, d's, and m's, where in terms of the sizes of the blocks and the degrees of the multi-degrees. So this is the part that I don't think it is feasible to go through, but I just want to give the shape of J of C. And the shape of J of C, and it depends on the number of free blocks, which is the W's, and the number of bound blocks. So number of free blocks is m, and the number of bound blocks is n. So it just depends on this division into m and n. And the main thing to observe is that it is a big conjunction of some, so the free blocks stay the same, but there are many copies, extra copies of the bound blocks. So, but in this formula, nothing appears that is, or all the polynomials that appear in this formula for G of C is already present in C, but of course they come with different bound blocks, and the number of these is determined by these indices, which I don't want to. So that's the shape. And that's why when I said that if you have in C, the complexity of C measured by the degree is at most D, then the complexity of G of C is measured by the maximum degree is still D. Of course, the number of polynomials, the size of C is bigger in the sense that there are more of them, of these polynomials, but these can be worked out, and one knows a bound exactly on the size of Jm of C, and it's not going to be, it's the size will depend on m and n, but not on degree. So there's no exponential blow up in the degree. Okay, and we'll denote by Jmn of V. And the realization of this, so this Jmn of V is an algebraic subset of a product of projective spaces, but in fact more of them than in the original for the original formula. Okay. And finally, this operator f omega, which is also kind of simple, it's built out of two very simple ingredients, namely the reciprocal of a given polynomial, but not exactly the reciprocal but the reciprocal modified by, well, you take the reciprocal of Q and subtract it from the Q of Pn. So that's what we call the rect n of Q, and just truncation. So this takes a polynomial of degree n mapping and truncates it to a polynomial of degree n. Yeah, so that's, so the operators f omega is built out of these two operations, and then we have omega, which corresponds to, so these, so there are n, so there are these n bound blocks. So now if you associate to each bound block a quantifier, namely exists or for all, so for each such omega, which is a map from 1 to n to this either existential or to universal, and you define f omega of I to be this operator, which is in terms of the reciprocal and truncation reciprocal if omega of I is the universal quantifier, and if just truncation multiplying by something and then truncating if omega of I is existential. And once again, I don't want you to try to digest the exact definition, but given a sequence of quantifiers, this f omega sequence of n quantifiers, then f omega is just the composition of these operators. And these operators are defined just in terms of the truncations and reciprocals as stated before. So those are the precise objects. So that's J and that's F. And with these, we have, so this C prime that I was saying in the beginning is that for any proper formula with n plus n blocks, but n blocks are free and n blocks are quantifier. And for each omega, which is a map from 1 to n to existential universal, you have Q of C omega, where, so C is just a formula without quantifiers, and now you stick in the quantifiers corresponding to this omega, then that's equal to f omega of Q of this. Notice that in the statement of the theorem, the Jm n of C does not depend on the sequence of quantifiers. This part does not depend on the sequence of quantifiers. The only dependence is through the operator f omega. So maybe just to show that this is kind of concrete, here's a very simple, maybe too simple an example. So here all the blocks are of size 2. So C of Wx x1 x2 defines a closed subset of P1 times P1 times P1. And if you look at this formula, it says that if you fix W with homogeneous coordinate 1, 1, then above it in the P1 times P1 corresponding to the two x's, you have over the first copy or the 0.11 of the first copy of x, you have the whole of P1. So this is, this part, the first part is isomorphic to P1. And the second part over the point with homogeneous coordinates 1, 2 of the W, you have a point. So you have, if you think of W as a base, which is a P1, so over the fiber over all points, most of the points in W is empty. And over the point 1, 1, you have a P1. And over the point 1, 2, you have just 1 point. Okay. Now, if we calculate the Ni, Di, Mi with the formulas, which I'm not going to do, but you have to trust me, then we obtain, first of all, that Q of J1 to C is this polynomial here, is a polynomial, even though it's a rational function. And then let's see. So if you have the quantifier that exists for all, so that means in the formula, the first, so there exists x1 for all x2, then the only point over which this is going to be satisfied is this one point here. So the Poincaré polynomial would be the Poincaré polynomial of a point. And if you take the other way, it would be for all x1 there exists x2. So this would define the empty set. So the Poincaré polynomial is going to be 0. And if you put two blocks, both existential, then in fact, both these points of, so the realization would be a union of 2 points. So the Poincaré polynomial will be 2. And now you take these formulas, and I did check with Maple that it turns out that f omega of q is as one expects. That is that f omega agrees, f omega of c of j of c agrees with q of c omega as expected. Okay, so that's as much as I want to say about the cohomological quantifier elimination. And let me mention just a few things where it comes from. So as I said, it comes from theorem that we prove for algebraic geometry. So if you have two non-empty closed subschemes or projective spaces, then there is a well-defined subscheme of P of n plus n plus 1, which is called the join of x and y, and it is very well studied. So if you just want to define the join in terms of equations, you can think that suppose x is given by a set of equations in PM, homogeneous equation in the x's, and y is given by a set of homogeneous equation in the y's in Pn, then the join of x and y is given by the same set. So you just take the union of the two equations, except that you treat the homogeneous coordinates of x of Pm juxtaposed with the homogeneous coordinates in Pn and think of them as a homogeneous coordinate. So now you have m plus 1 plus n plus 1 and think, so that's n plus 2 homogeneous coordinates, and think of it as a homogeneous coordinate in n plus n plus p n plus n plus 1. So the join of x and y is given by the same. It's not a good way to define it, but if you want to see it in terms of equation, it's given by the same set of equations defining x and y, and then forgetting the fact that the first set is homogeneous in x and second set is homogeneous in y, and think of it as homogeneous, all these equations homogeneous in n plus 1. And then one can show that whatever, so this is the algebraic join. So one should, of course, so there's a distinction between this rule join and the topological, what one topologist would call a join, which is really, if x and y are two spaces, then the join of x and y is obtained by taking the union of segments joining points of x and points of y, disjoint copies. And if you want to see this as kind of this topological analog, then instead of connecting points in x and y by segments, you are using P1 to connect each point in x to each point in y. But okay. So one can show that this algebraic join is connected. And one can interpret this connectivity result as saying that the restriction map from the zeroth cohomology to the zeroth cohomology is an isomorphism. So our main theorem is really generalization, higher dimensional generalization of this fact that if you have now non-empty closed subschemes of some projective spaces, then you can define the join in the same way for not just for 2, but for any number. And then we show that and you can define not just, so the p-fold join, and we show that the restriction homomorphism is injective for, is an isomorphism for all dimensions strictly less than p and injective for j equals p. And here, as I said, the cohomology is taken to be L-adic Ital cohomology with L some prime not equal to the characteristic of the base field. Let me skip this and let me mention a few things. So the topological connectivity properties in the Zariski topology of joints of projective variety is a classical subject studied by various authors. And the main emphasis in these works was on studying the notion of deconnectedness of Grothendieck. So projective variety is said to be deconnected if the dimension of the variety is bigger than d and x subtracted y is connected for all closed subvarieties of dimensions strictly smaller than d. And it is a classical result in algebraic geometry that if x is deconnected and y is e-connected, then the join is d plus e plus 1 connected. So this goes in this sense that join should be very much connected. If x is connected and y is connected, the join is even more connected. But this result, while being philosophically similar, is not, so we cannot infer our cohomological connectivity from this result. And moreover, what we actually need is not the absolute version, but a relative version of our connectedness theorem, which has no analogy with this Grothendieck connectivity type theorems. And this relative version is in fact the key to our connectivity theorem. And this is what relates. So one should think of this. So we are taking schemes which are relative to a base scheme S, but let's forget about this. Let's say let S to be equal to Pm. And so X is a subscheme of Pn times Pm and pi the projection. So the key result about the Poincaré polynomial that we need is the P of the relative p-fold join of X. So by topologically, you should think of this relative to S join is as if you are taking fiber-wise, because you have this projection, so you are taking fiber-wise a p-fold join of the fiber. But this is the algebraic geometric way of doing this fiber-wise join, is to take the relative join. And so the Poincaré polynomial of this relative join is related to the Poincaré polynomial of the image of the projection by this relation, which holds mod t raised to p. And now you can invert this part and you can take it here. So it's Poincaré polynomial divided by 1 minus t square up mod t raised to p. So sorry, so this part is 1 minus t, so you can multiply this by 1 minus t square, and that will be equal to the Poincaré polynomial of pi of x mod t raised to p. And this is what allows us to recover the Poincaré polynomial of the image from the Poincaré polynomial of the relative join, of course, mod t raised to p. So higher, as you want more and more Betti numbers, you have to increase p. Okay, so that's more or less what I wanted to talk. I am already 3 minutes above my time, so let me end here, and I'm happy to take any questions.
So are there any questions?
Can I ask one question? So,
Yeah, go ahead, Min.
so there was one thing that I'm still somewhat confused about. So early on, so we do know that if you are taking a closed subset of a projective space,
Yes.
and one take the projection down to a lower dimension projective space, that will
Yes.
continue to be closed.
Yes.
Right. So when you have an actual quantifier elimination, and then why is there a need to go to this Poincaré kind of quantifier elimination? Maybe the question is not doesn't make any sense.
Yes. So yeah. So that's what I addressed. Maybe in this incidence variety theorem. So so we had the image which is indeed closed, and in this case hypersurface given by one equation.
I see.
And but the thing is that this equation has a pretty big degree in relative to the degree d, which is the defining polynomial of the given formula. Well, all these are of degree at most d in x and 1 in the f's. So the quantifier free version suffers from the fact that it's difficult to compute, and in fact, it's related to the p versus np problem in computational complexity. And in this case, the degree is unavoidable. On the other hand, if we replace it by this j of phi of dn, which is a weaker version, this polynomial has this formula has polynomials only bounded by d, which is the same degree bound as in the original case. Of course, the property is much weaker, namely, instead of the realization of the two becomes same, we only have that the q of the realization is the q of the nu up to this operator f. So it only makes sense once you think in terms of the complexity of the formulas involved. Otherwise, as I said, that you could as well take in this formula C prime to be the classical eliminant, and you don't even need this f of omega because Q would be equal because the realizations are the same. I hope that answered your question.
Yeah, thanks very much. Yeah, it does.
Oh, we have a question from the in-person audience.
Is there something special about this pseudo-Poincaré polynomial, or there are other polynomials that maybe you can do something similar with?
Yes, I do not know. It's the one that seemed to work, maybe because of the properties of projective space. And by the way, I should also mention, if for generalizations of this thing, well, other polynomial is another, I don't know. And maybe one can think of, if one is interested, for such results over other structures, for example, over the p-adics or valued fields, which we do not know how to do. I believe that one can do this over O-minimal structures.
So I had a question. I think
Yeah.
on one of the early slides, you mentioned like computing VC densities as an application. So were you able to do that for any new, or is that an application of the new machinery or?
No, this is just a statement of things where I have personally been involved in or have seen topological methods used in model
Oh,
theory and combinatorics.
I see.
So
Ah,
yeah,
okay.
so this is not related to what I was talking today, but
Oh, I see. Okay. Yeah. Got it. Okay. Are there any other questions?
I have another question.
Mhm.
So the first theorem is in terms of this pseudo-Poincaré polynomial. But what is your last theorem about actually Poincaré polynomial? So it's
the last one is about the Poincaré polynomial. Sorry.
So it won't be about pseudo-Poincaré anymore.
No, the connectivity theorem, from the result that we prove in algebraic geometry is about the Poincaré polynomial. The reason why the pseudo-Poincaré polynomial enters is because of difficulties with respect to alternation of the universal and the existential quantifiers. And this is kind of a technical artifact of, but the connectivity result is this is just about the Poincaré polynomial and not about the pseudo-Poincaré polynomial. So that's, and also this result has some other applications. For example, you might want to use it to bound the Berry numbers of pi of x in terms of the Berry numbers of x, or in terms of the degrees of polynomials defining x. And in some cases, it should produce better bounds than methods that have been used till now. And that's because it's really about Poincaré polynomial, not the pseudo.
Okay, if there's no more questions, let's thank Saugata again.
Thank you.